here, I think, 5 years ago.
Yeah.
Thanks very much.
Great, thank you. Cheers. Thank you. It is lovely to be back. It was 2015, I think I was here before. I always feel slightly like there's a great opening to a stand-up comedy routine where they say you play Auckland twice in your career, once on the way up, and it's really good to be back. So but I was very excited to come and talk. I remember being here with great fondness last time, so I will do my best to entertain you this evening. What I want to talk about is a whole range of things, but they're united under a banner of the fact that astronomers, contrary to our reputation, typically don't know what we're doing. If there's one thing you take away from tonight, please take that away. I'll try and demonstrate that without falling off the edge of the stage, which is looking a bit precipitous here. What I mean is this: when I tell people that I'm an astronomer, I get a few reactions. I get, especially in the UK, I get asked if I've met Brian Cox. The answer is yes. The second most common reaction is that I get asked if I found aliens. The answer's no, though we'll get back to that later on. But then the third reaction is really odd, which is that if you say you're an astronomer or that you're interested in astronomy, people say things like, you must be really clever, or I was terrible at that at school. There's this instinctive reaction. And I think it's partly driven by the fact that when we talk to our friends, our neighbours, our colleagues, to audiences about what we've been doing, we often give the punchline, the ending, what we found out, and we forget that the road to these great discoveries is often one of accident and upset. So I want to really tell some stories about being surprised by the universe. And these can be small-scale things as well. We've all been hugely enjoying our new Christmas present. This is the JWST, which I like to think of as the Just Wonderful Space Telescope, which launched on Christmas Day 2021. And to everyone's surprise, actually worked. This is the largest telescope of its kind ever sent into space. This mirror is 6.5 meters across. There are a couple of people down here for scale. And it had to be folded up to fit into the rocket. And there were over 300 separate things that had to go right, single point failures that had to work in order for this telescope to deploy successfully. From unfolding the main mirror, to spreading out a lawn tennis court-sized sun shield, to the deployment of tiny optical pieces and components so that the cameras work. And everything worked brilliantly, and the telescope is now driving a revolution in astronomy. It's an infrared telescope, and it's letting us see things in the universe that we haven't seen before. And, almost as importantly, given that it was paid for by the American, European, and Canadian taxpayers, it's producing beautiful images, which I think is as we know, is part of the joy of astronomy. And this was one of the first images that was released. It's of a planetary nebula, so this is the outer shells of a dying sun-like star. The star's actually not this one, it's buried in here somewhere. It's a rather beautiful image, but it's also an example of the kind of serendipity that I like in our subject, and it comes from this part of the object here. So as soon as this came down to mission control, the astronomers who were working there started wondering what this thing was. And the initial thought was that it must be part of the nebula. It's pointing almost exactly to the center. And so they thought maybe it was something that had been ejected from the center or some strange linear feature. So you start arguing about how this has been sculpted to produce this sort of straight line feature, which is unusual for a planetary nebula. I see I've circled it for talks where I don't have to point at it. But actually, it's, I think, more interesting, but also more easily explained than that. If you look at a different wavelength, so JWST can look in different colors, just as Hubble can, then that galaxy, sorry, I've given it away now, that object appears outside the nebula. It's actually a distant galaxy that just happens to be in the background. So that's the explanation for it. But we can now use it because Now we know that this is a galaxy. We understand what galaxies look like. So we know that when we look in this color, we're getting the galaxy plus the nebula. So this is like shining a flashlight, shining a torch through the outer edge of the nebula. And so we're able to study the dust and the behavior of the nebula differently because we've got a nice handy galaxy sitting conveniently in the background. A little bit of luck that enables us to understand the universe in a different way. Now this galaxy, although it'll be used for this, it probably won't get a name. It's got a catalogue number, but I guess we could say that the people who took this image discovered that galaxy. And my interest in discovery and surprise goes back a long way till to the time that I was a kid in an astronomical society like this one in Torbay in South Devon, in the southwest of England. I desperately, as soon as I got my first telescope, which is a 6-inch reflector that I've still got today, no motors, no drive, nothing, just something you can plonk down and point at the sky, I was obsessed with trying to discover something. I was particularly keen, still am really, I wanted to discover a comet, because comets are named after the discoverer. If you find an asteroid, you've got to name it after somebody else. Galaxies have catalogue numbers, but comet Lintott, I think, feels pretty good. If anyone's got a spare comet and doesn't mind handing it over, that would be great. But I didn't find a comet. I wasn't really equipped for it at the time. There was one evening that I remember where I was doing my favourite thing, which is looking at the Orion Nebula. The Orion Nebula, as I'm sure many of you know, is our nearest star-forming region. And what I love about it is that even in a small telescope, if you're patient and you have dark skies and you allow your eyes to get used to the dark and wait for those moments where the sky is still above your telescope, then you can see detail in it. You can see the shape of the gas as it curls round the young stars that are formed within the nebula and whose light is responsible for making the nebula light up. So you get a real sense of what's going on. There's a great William Herschel, the great English observer who discovered Uranus, described it as an unformed fiery mist containing the material of countless future suns. And so I love looking at the Orion Nebula and thinking about these things and trying to see more detail even through a small telescope. But on this particular evening, I was doing this and I nudged the telescope. And it moved, and just above the nebula, just to the north of the nebula, that's below from here, I suppose, there's this site, and this cluster appeared in the eyepiece. I didn't know that there was a cluster next to the Orion Nebula, and it was particularly striking. I had about this field of view, and I went and looked. It's going to be difficult for the younger members of the audience. We didn't have the internet at home, and so I went and got a book, which is like the internet but slower. So I got a Star Atlas out, and Sky Atlas 2000 doesn't have this cluster marked. And I remember getting a pencil and putting a cross and writing Lintott 1 next to this thing. And when I got to school, I found out this is actually NGC 1981. It's been known since the 17th century. It's not a new discovery, though I still think of it as Lintott 1. And if you're looking at the Orion Nebula, I recommend it's a rather lovely cluster in a wide field and a small telescope. Look at it and think of me. But from that point, I sort of thought that I'd misunderstood astronomy, that I thought discovery was over. I grew up, went to university, started working professionally, and I started to realise that instead of taking data, a lot of astronomy in the 21st century is about using data that already exists, produced by machines like this one. This is the Sloan Digital Sky Survey. So this is a 2-meter class telescope. It's on a site in New Mexico that was chosen because it has 330 clear nights a year, which I think is about the same as Auckland from talking to some of you at the weekend. But it's in the north. And Sloan is a remarkable thing. It's what happens when you let particle physicists build you a telescope. So astronomers were used to dealing with observatories. Like JWST was built to do galaxies and exoplanets and star formation and even some solar system stuff. This was an experiment. It did one thing very well for 8 years, and what that was it pointed at the sky and it allowed the sky to turn over it. And as each patch of sky scanned across the telescope's field of view, it took a series of images in different filters, so that you got a colour image of the sky. That recorded several billion objects, most of them stars, but about 1 million of them were distant galaxies. And on very clear nights, Sloan went back to those distant galaxies and it measured their distance as well. And so what this means is that we got a three-dimensional map of our local universe. And so let me show you that. Steve, there's a possibility this will play awful guitar music. We should kill the awful guitar music a bit. You've muted it already? Great. Actually, that's just crashed my computer, which is slightly worrying. This is not part of the thing about astronomers not being competent, by the way. This is just ordinary incompetence. Hang on. This is going to be upsetting. Keynote cannot be opened. Okay. This might get interesting. Okay. It's okay. Don't panic yet. We're good.
You good?
It's definitely me, not you. Yeah. No, that's a different talk. Okay. Yeah, no, it's okay.
Resident IT geek.
Yeah, no, it's okay. I think that was just a Mac flub. All right. We'll try this again, and if this doesn't work, you're going to have to just imagine a 3D view of the universe, okay? So, there we go. See, plonky guitar music. There we go. So we started on the Milky Way, and we're traveling outwards through space. And this is real data. I know this looks like a screensaver, but these are real images of the galaxies at their right points in the cosmos. And this is a fabulous map. It showed us really something that we suspected but hadn't seen in detail, which is that the universe on large scales is lumpy. There are places with loads of galaxies, places with very few galaxies. We were just talking about the cosmic web, which is the slightly poetic name that we give to this. You can see, for example, here there is a large feature, this sort of C-shaped feature, which is called the Sloan Great Wall, which might be the biggest thing in the universe. With a few 100,000 galaxies as part of it. We'll stop the whole universe and rotate it for you in a second. And you'll really get a sense of the fact that there's this honeycomb structure. Ignore the fact that there's nothing here and here. Those are the bits of the map we haven't filled in yet, mainly because our galaxy gets in the way. But you get a real sense of this 3D structure. And so this is an incredible data set, the result of 8 years and more than 1,000 nights observing. And what they did with it was take all of this data, the point of the project was take all of that data and write this paper. The completed SDSS-4 extended baryon oscillation spectroscopic survey, measurement of the BAO and growth rate of structure of the emission line galaxy sample from the anisotropic power spectrum between redshift 0.6 and 0.1, 1.1. Now, I know from my previous visit that you're all on top of this stuff. So I'll just show you the graph that's crucial. There it is. That's all of the data from the survey collapsed down into a single graph. And the point is really that this wiggle is a measuring rule that helps us understand the scale of the universe and how it's been expanding. So this is a worthwhile bit of cosmology. But I think it's slightly sad to only take your million galaxies and reduce them to a single graph because you miss the fact that some of them look like penguins. And one of my points this evening is that both responses to the data are useful, right? And both are fine. We need to do both sorts of astronomy. We can do our cosmology and measure the scale of the universe, but we can also ask questions like, why does this galaxy look like a penguin? Does the egg have anything to do with it? What's this dust lane doing and why is it so thin? Is this part of the same system or is this different? Why is there star formation? The bright blue stuff is star formation. Why is the star formation concentrated around the edge of the galaxy? Is this a disk that we're looking at? Or is it some sort of weirder shaped system? What will happen to this in the future? All of these things are interesting and valid questions, and they come from finding unusual objects in the data. And so when we have large data sets, we can do both things. We can do the physics and the experiment that we set out to do, but because Sloan happened to take excellent images, we can also do this sort of penguinology on a galactic scale. And so surprise is important, and whenever, in fact, we've had large data sets or new sets of ways of looking at the sky, we've discovered new things that have surprised us. So take, for example, the history of radio astronomy. The 20th century will be remembered, I think, in the history of science for the great expansion of astronomy beyond the kind of light that we can see with our eyes and into other wavelengths like radio astronomy. This is Grote Reber. He was the second great pioneer of radio astronomy. The first was a chap called Karl Jansky, who built a pioneering instrument that had detected what he charmingly called star noise coming from the universe. And Rabe heard a broadcast of star noise on National Public Radio in the US. He was he was an engineer by trade, an electronic engineer, and he decided he was going to devote his life to working on this stuff. And so he wrote to every astronomer in the US, this is the 1930s, saying that he would like to offer his skills and his services. And all of them either ignored him or wrote back and tell him that there was nothing interesting to do in radio astronomy. Rabe was a man who wasn't to be put off, so he just built his own telescope. This is his telescope. It was the first steerable dish used for radio astronomy. This is actually next to his house in suburban Illinois, about 70 miles outside of Chicago. And what he would do is go to work and come back and observe at night. And he'd have a couple of hours sleep, go to work, come back and observe at night. There were a couple of good reasons for doing that. One was obviously he was working in the daytime. The other was that it turned out the major source of local interference were spark plugs in cars. And so his observing was better when everyone else was asleep. And the third one, and this is true, is that his mother used to hang her washing on the telescope during the day, which interferes with your radio observations. Also, the radio observations interfere with the washing, and it's not clear which of those two is more important. But Rabe made remarkable discoveries with this thing. He produced the first proper map of the Milky Way. This is from a paper that he published in 1944, actually almost over the dead bodies of the astronomical establishment. He wrote up his observations, his maps of the Milky Way, which are the first to show, these lumps here are the spiral arms. So he was the first to show that the Milky Way was a spiral galaxy, and therefore rather like the spiral galaxies that we could see. But he wrote up all of this information and sent it to the main journal, the Astrophysical Journal in the States. And rather than publishing it, the editors got a group of professionals together to come down to Illinois and see if this guy was for real. And they went away impressed, but they refused to let him publish on his ideas about what he was seeing. So if you look up this paper, the map is there, but not the submitted version, which includes his explanation that says that this is because the Milky Way is a spiral galaxy and so on. So he wasn't allowed to publish because he was seen as being outside the astronomical firmament, really. I could go on about Rabe. There's a whole talk to be given about him. He's an extremely interesting man. He's an iconoclast. He ends up with a job at Bell Labs, thinking about building the world's largest radio telescopes, gets upset that they're not funding him enough, goes on holiday to Hawaii and doesn't come back. He ends up living in Tasmania, running his own radio telescopes, developing his own slightly unconventional histories of cosmology. But he still had enough pull in the 80s. And I really like this story, that he had a theory that the only reason his telescopes weren't giving him the results he needed to prove all of physics wrong and to back his cosmology was that the Earth's atmosphere was getting in the way. And he worked out that if somebody could detonate a small nuclear bomb above his observatory, then he'd be able to see clearly into the cosmos. So he wrote to the Australian, British, French, and American governments requesting a small bomb. He wasn't given one, but somehow he still had enough pull and was famous enough that what happened instead was that the space shuttle, while it was re-entering the atmosphere above his house, fired its engines to try and affect the ionosphere above his radio telescope and see if they could improve it for him. I love the idea. Can you imagine having the kind of career where NASA will get the space shuttle to fire its engines to try and prove your pet cosmology theory, right? It didn't work, but that's not the point. The great tale of serendipity in radio astronomy comes a little bit later on my side of the world in Cambridge with this ridiculous-looking experiment. Ignore the dish in the corner. The telescope which made the discovery that I'm talking about is this field of antennae here. It's built out of chicken wire and not much else, really. And it was built by a team led by Anthony Hewish, but used by this woman. This is Jocelyn Bell, now Jocelyn Bell Burnell, who was a PhD student using this antenna to try and answer what was a fundamental question. By this stage, radio astronomers had seen that the sky was full of what they called radio stars. there were sources of radio, individual sources of radio light coming from various positions in the heavens. And the argument was whether these things were distant or nearby. We knew they were beyond the solar system. That's all we knew. And Jocelyn's PhD was to actually look at whether they were twinkling or not. In the radio, it's called scintillation, but it's really twinkling. The twinkling of a source tells you how big it is on the sky, and that would tell you whether it's a nearby thing or a distant thing. Distant things should only be point sources. So this is what she was working on. What this actually meant, once the thing was up and running, was that all of the data from this would be fed into a small shed. This is it over here. The observer would sit in the shed and watch as graph paper came out of a machine with a pen moving up and down to record the strength of the radio signal as the sky passed overhead. Jocelyn was doing this one evening. This is the actual data, this is the actual sheet, and this is the signal from the telescope, and she noticed just this, which she called a little bit of scruff, like no more than a scribble on the page. And the remarkable thing to me about this is that, here is a similar bit of scruff, but this was recognised as interference. This shape was the kind of thing that happened all the time because somebody drove a car past or whatever. But she realised that this was unusual. And better than that, she realised something in the back of her head, because she'd spent so long looking at this sort of data, something in the back of her head told her that she'd seen this before. And so she went back through all the charts for all the times that that bit of sky had been overhead, and she found 2 more examples. So this is a thing that repeated, and they were able to systematically observe it. And this is a remarkable source. It was rotating very rapidly, so it was pulsing very rapidly, several tens of times a second, I think, for this one. And nothing was known that could create such a signal. There's a sidebar to the story, which is that the team, as a joke mostly, called the signal LGM1, which stands for Little Green Men 1, because the idea was that this is the kind of signal that intelligence produces, right? It's a signal. There's a great story about an American astronomer who was visiting at the time and was happily chatting to somebody in their office and noticed a box file on the wall that said Little Green Men 1 on the label. And the Cambridge researcher spotted that his visitor had clocked this and just slowly turned it round, and it wasn't commented on. They were very relieved. They found later on 2 or 3 more of these, and were very relieved, therefore. They didn't think they felt that ruled out the alien hypothesis. I'm not quite sure that it does. Which is a great relief, particularly to Jocelyn, who remembers cycling home from Cambridge, from the observatory out of town, into the centre of town, being annoyed that the aliens were getting in the way of her PhD. I think it's a measure of the woman that she may have discovered alien life and she was annoyed it was getting in the way of her physics. This is the kind of attitude that we need, I think. As many of you know, this turned out to be the pulsar at the heart of the Crab Nebula. It's the remnant, this is the Crab. Right in the middle here is a dense remnant of a massive star, a neutron star, in fact, that's rapidly spinning. And what that means is that there are a couple of jets on this object that's probably not much bigger than the Earth, and there are these jets, and as the thing spins rapidly, it pumps energy out into the nebula. And this is an X-ray view where you can see the effect the pulsar is having on its surroundings. And we see it as a pulse because we think that the magnetic fields around this thing focus the emission into these 2 beams of light like a lighthouse. And so we see a blink every time one of the beams crosses Earth. Thousands of these things are now known. They've been responsible for all sorts of things like testing general relativity, mapping the galaxy, and helping us understand some really quite strange physics that happens in these densest of objects. But they started with Jocelyn paying attention to a small patch of scruff that wasn't anything to do with her research. So she's assigned to me that you have to be willing to be surprised. It would have been very, very, very easy for her to just ignore that little patch and get on with what she was supposed to be doing. But great science comes from accidents when people are prepared to pay attention to them. There's a great tradition of radio astronomers now paying attention to things that change in the radio sky. One of my favourite stories is from this place. This is, of course, the Parkes Radio Telescope, the dish, over in Australia. And the great story about Parkes and the changing radio sky came about just after about 10 years ago now, just after they'd upgraded their equipment. They started to see bursts of radio waves coming from various parts of the sky. They called them peritons. And these were always the same frequency, but they came from all over the sky, and that suggested that they were coming from distant galaxies. If they were coming from the solar system or the Milky Way, they would follow the plane of the solar system where the planets are, or the plane of the Milky Way, but they were coming from all over the place. And so this is very exciting. If they're coming from distant galaxies, they're probably very powerful bursts of radio waves. So some energetic process is at work, maybe something involving black holes or colliding neutron stars or so on. So this caused a great degree of excitement at Parkes. They published the results. Other radio telescopes tuned to the right frequency and went looking for these things, but no one else could see them. It's okay. Parkes had just upgraded their equipment. They were confident that they had the best receivers and the finest software in the land. And it wasn't until they published a paper on a catalogue of about the first 100 of these things that the wheels really came off the story, because that paper was seen by a wide number of people, including somebody who noticed that there was something odd about this graph. This is the time of day that the peritons were seen. And as you can see, there's a spike somewhere around the middle of the day. And this is really odd, because distant galaxies don't know whether it's lunchtime in Canberra, we assume. And certainly it would be weird if they cared. And so something else is going on here. And the paper was seen by a retired microwave engineer, not microwave detecting the universe in microwaves as in, I need to reheat my curry from last night microwaves. And he said, I know what these things are. Turned out the microwave in the visitors center had been malfunctioning. In fact, what had happened was, when you open, if you're impatient and you open the door of the microwave before it's gone ping, there should be a safety device that shuts off the microwave instantly. That was broken. And so only when somebody, not every time, but only when somebody was impatient in the visitors center, this thing would emit a burst of microwaves, which the telescope would pick up on. And so I like this story because it's funny. Also, I met somebody, I gave a version of this talk a few months ago, and I met somebody who'd spent a summer as an intern at Jodrell Bank, the radio observatory outside Manchester, where his task was to try and break microwaves in such a way that they would replicate this result. So he had a photo of himself surrounded by a field of microwaves that he'd taken hammers to. But I think the lesson from this for me is that you should plot all the things. If you'd made this plot earlier, you would have noticed, several of you in the audience when I put this up realized something was up, right? So they had this data, but why would you plot the local time? That doesn't seem relevant. Anyway, it's a good story, but it also inspired people, because people had started thinking about how to find flashes of radio waves. And it's now become a very interesting part of science. So a group of students led by now Professor Duncan Lorimer were looking through archived data from a different Australian survey. They were looking for pulsars, the things that Jocelyn found, in the small Magellanic Cloud, because distant pulsars in a dwarf galaxy in orbit around the Milky Way would be really interesting. We can see whether they're different from the Milky Way ones. We can see perhaps something of the properties of the SMC. And what they found instead was this. So this is what's called a waterfall plot. So this is a good way of looking at radio data. So this is the frequency of the signal. And modern radio telescopes are tuned to a wide band at the same time. And then this is just time. So, and then the color, the dark, where you see dark, there's a signal. So there's a huge amount of noise. That's why you've got this sort of magic eye pattern here. But this stripe is a very, very strong signal. It was so strong it basically blew out the receiver. But it had sat in the archives for 6 years, this signal, without anyone finding it. And it was only when they went back and looked to see if there were any bursts through radio waves that they found one. The characteristics of this sort of thing are that it's a burst of radio waves. So it's bursty, it's in the radio, and they don't last very long. So using astronomers' usual methods of naming, this is now called a fast radio burst, because it's fast and it's a burst of radio waves. It actually seemed to be coming from just, this is the SMC, it actually came from down here, so just off the galaxy. There are now hundreds of these things known, and they turn out to be a common feature of the universe, and they're a little mysterious. We know that they seem to come from distant galaxies, though we have seen one from the Milky Way. Some of them repeat, but they often repeat at different frequencies, which is odd. One of them repeats regularly every 16.4 hours, but only that one. And we've got very good at seeing these things. In particular, this thing, this is CHIME, which is a Canadian radio telescope that was built to do cosmology, to look at the early universe. But it turns out, accidentally, it's really good at finding these fast radio bursts. And so CHIME is finding hundreds of these things, including, there's one in the galaxy M81, which is a relatively nearby galaxy. And that's one of these ones that repeats. And so using other telescopes, we've been able to get a really precise coordinates for where it is. And it seems to be coming from within a globular cluster in M81, which means it's coming from old stars. So maybe that's a clue as to what these things are. There's also at least one of the other repeaters that seems to be in a double star system. But we're really kind of clueless, as people have evoked black holes colliding, neutron stars colliding, something called magnetars, which are neutron stars with strong magnetic fields. We don't really know what causes these things, but we're having great fun arguing about them and trying to find more of them. But they started with people realizing they should look for things that weren't expected in the data, just as I've been proposing. I want to switch scales now. I've mostly been talking about observations of galaxies and nearby galaxies, but I think this sort of surprise and the potential of the universe to surprise us exists on larger scales as well. These two are responsible, I think, for the biggest surprise of 20th century physics. This is Penzias and Wilson in front of the Holmdel antenna. This giant ice cream scoop thing was a sensitive radio antenna. They worked for Bell Labs, and their aim was to establish what the cause of background noise in the radio was. The kind of noise that would interfere with, for example, your desire to send a transmission across the Atlantic or across the Pacific. So they had this antenna. I don't know if you can see, but it's on a train track so that you can rotate it. And after much painstaking work, they worked out that most of the noise was due to distant thunderstorms at the frequencies that they were working on. So when they pointed this towards even places where storms were happening hundreds of miles away, they picked up this signal. But they found that 5% of the noise couldn't be accounted for in that way. And I think most people would have declared the job a good one, said, we now know that most of the noise is thunderstorms, 5% remain, you can write the paper yourself, 5% remains in residual other sources. You know, I'll worry about that later. These two didn't. They went to great lengths to try and work out what the signal was, and they thought they had an idea, which was that they suddenly realized one morning that their antenna was covered in what they describe in the paper as a white dielectric substance. It was a substance that had been deposited by pigeons that had taken up residence within the antenna. And so the pigeons had to be dealt with. This is the pigeon trap that they used. And this thing is in the collection of the Smithsonian Museum. It's my second favorite object in their collection, and they will show it to you. If you turn up in DC and ask to see the pigeon trap, they will get it out for you. Anyway, I want you to imagine that these two highly distinguished engineers, who I assume weren't wearing suits at the time, used the pigeon trap to capture the pigeons. We're going to assume that the pigeons were taken a long way away and released. Let's just assume that that's what happened. Pigeons come back, I know, but they're living happily somewhere. And then they scrubbed the antenna clean with toothbrushes. And I want you to imagine that you've done that, and then you go back into the receiver cabin, and then you switch it on, and then you discover that this tiny hiss, this 5% hiss, is still there. And I want you to imagine caring at that point about what it was. One of the weird things about it is that it came from all directions. It didn't seem to change. And so they eventually realized that this was nothing to do with Earth, but had to be a cosmic background. We now call it the cosmic microwave background. and it's the oldest light in the universe. So it's light that was emitted at a time when the universe was about 400,000 years old, and it's been traveling through space ever since. And we can even, thanks to people like Charlie Lineweaver, who was the other guest at the RAS conference at the weekend, we now know that there are tiny fluctuations in it. So this is a modern map of that microwave background, where the red bits are slightly warmer and the blue bits are slightly colder than the average. And that translates to places that are slightly denser and slightly less dense than the average. Not by much, it's about 1 part in 10,000 at the early universe. So the early universe is smooth, but not quite smooth. And it turns out that these tiny fluctuations are the seeds for the cosmic web, the structure that we saw in the Sloan survey. Because if I show you what happens, we can simulate this in a supercomputer. But if we start off with a universe where we've made it as lumpy as we see from the microwave background, so in this visualization, bright bits have more stuff than dark bits, then what happens if I allow this to evolve over time is that the rich get richer and the poor get poorer. The bits that already have slightly more stuff have a slightly stronger gravitational pull on their surroundings than their less dense neighbours. And so material will tend to move towards the places that already are overdense. And so what start off as these really tiny fluctuations, as we go for 1 billion years into the universe's history, into 5 billion years, and then almost up to today, you end up exaggerating these tiny differences so that you produce the cosmic web that we see today. I can run it as a movie, and I've taken the expansion of the universe out here, so we don't have to worry about it. But what you can see over time is that you start to build up this web structure with these empty voids, these big clusters in the middle, and then this structure. But it comes from these tiny fluctuations that were seen in the microwave background. And so when those fluctuations were first seen in 1992, we suddenly thought we had a framework for explaining the long history of structure in the universe. But people wanted to be able to test this, to be able to see it happen. One of the great joys of astronomy is that we can see the past, because when we look into the distant universe, we're looking at objects whose light has taken billions of years to reach us. We see them as they were billions of years ago. And so if I want to know what the early universe was like, I just need to look far enough away that I'm seeing galaxies whose light has been traveling towards us since that early part of the universe. And the first people to really realize the potential of this were a group of astronomers using the then new Hubble Space Telescope in the mid-90s. Hubble's a marvelous instrument, an optical telescope in space, decades in the planning. And though it had some teething troubles when it was first launched, by the mid-90s it was working really well, and it was competitive to get time on it. It still is. You have to apply if you want to use Hubble. Anyone in the world can do this, but you have to write up a case as to why you want to use it and explain exactly what you'll do with precious time. And so when a group of researchers proposed to take the longest allocation of Hubble time, they wanted 2 weeks of Hubble time. If I get 90 minutes, then that's a good year. And a student can spend a year working on a 90-minute allocation. So that's 1 or 2 observations. But they wanted 2 weeks of time. And what they proposed to do was to look at a particular patch of sky in the northern hemisphere, just above the plough. But they picked that patch of sky because there was absolutely nothing there. And their idea was that they would just stare at nothing and hope to capture faint objects that couldn't otherwise be seen. I don't think they were considered crazy, but it was considered that this was really terrible PR. Hubble had just gone through trouble. It was broken on launch, had to be repaired by space shuttle astronauts, and was only just functioning. I don't think NASA fancied the headline of Hubble stares at nothing. There are all these other things we could do which are guaranteed to succeed. There were also some eminent scientists who had calculated that Hubble wouldn't see anything new if you did this. But it turns out there's another way of getting Hubble time. Like all big observatories, a tiny amount of their time is in the personal gift of the director of the observatory. So they can do whatever they like. And they do that for a set of reasons. And the guy who was in charge, Bob Williams, had a problem. His staff were knackered. They'd been learning how to use this telescope. They all really needed a break. But you can't shut down your multi-billion-dollar telescope because people need a break. And so what he decided to do was he decided that over Christmas in 1995, he wanted to make the simplest set of observations he could think of. And the simplest set of observations is just to look at the same patch of sky again and again and again and again and again. So he decided he was going to use almost all of his time to make what we now know of as the Hubble Deep Field. And it was released just a few days after the observations had finished. And this is the result. Almost everything you can see in this image is a galaxy that hadn't been known before. Turns out when you stare at the distant universe, it comes to life. So I think there are 4 stars in this image, possibly only 3, but every other dot is a distant galaxy. And so suddenly we could test some of the predictions of this model. We thought that early galaxies should be smaller than the ones locally. They should be more clustered together because they're in this cosmic web that hasn't yet assembled. They should be peculiar, and lots of them are quite odd. They don't really look like the galaxies that we see today. And so a huge amount of work has been done with the Hubble Deep Field, and this has become a standard thing that people do with new telescopes. You just point them at this patch of sky. There's now one in the constellation of Fornax that almost every telescope has looked at as well, and you get a view of the distant universe. And so it's no surprise that people have done this with JWST. In fact, they've done this so well that JWST is such a good telescope that you get this for free. So this was another of the first images that were released, and what the scientists were trying to do was take an image of this galaxy cluster, these yellow galaxies here, because this is a known gravitational lens. The gravity of this galaxy cluster bends the light that's coming from things behind it, and it magnifies them. So these arcs are distant galaxies whose light is being magnified by this galaxy cluster. It does distort them. You can see this one here, it has had a particularly bad time. This is what's happened to this. The actual technical word for this is that the galaxy has been slugified, which I quite like. But you can reconstruct what's happening in these galaxies. But almost all the excitement in this image has been that almost anywhere else you look, there are loads of background galaxies. In particular, people got very excited about a set of red dots that appeared in this image. I can never find one. There we go. So this is the most exciting thing in this image. I'll zoom in for you, because we've spared no expense. Here you go. Genuinely, that's the best image of this thing that we've got. But these red dots turn out to be galaxies. This one, we're seeing this as it was less than 1 billion years after the Big Bang. So we're seeing, for the first time, the first galaxies. Here's another couple of them here. This one, I think, is 650 million years after the Big Bang. And this one may be just 350 million years after the Big Bang. Million, not billion. And so we're really beginning to see the early galaxies, and there are too many of them, as you might have suspected from the fact that I'm surprised that they're there. As we've begun to count these things up, we think that galaxies in the early universe are more numerous than we expected. These are all provisional results, by the way, so there should be an asterisk next to all of these. But it's looking like there are more of these than we expected. They're more massive than we expected. They have larger black holes than we expected. And if that set of results holds up, probably by the end of this calendar year, we'll know whether all of those statements are actually true or not. There's some worry that maybe these are actually local galaxies masquerading as distant ones, but there are ways of checking. If all of those things hold up, then there's something we don't understand about our story of the universe. Either our cosmology is wrong, the details in how we think the universe has begun to evolve, or we don't understand galaxies as well as we thought we did. But it's a story that starts with just pointing a telescope at nothing and paying attention to small red dots, which I think is really exciting. How long do I have left? All right. Do flee. I couldn't decide what to talk about, so apparently I decided to talk about everything. Let's just keep going. I can't talk about galaxies really without mentioning another way of understanding these distant galaxies is to find their local equivalents as well. So if you think that your early galaxies are unusual, the other game we can play is look around us and ask which galaxies near us are like the ones we see in the early universe. And I've done that in particular through a project that was mentioned in the introduction, Galaxy Zoo. And this is a project online that invites anyone to come online and help us sort galaxies by their shape. The shape of a galaxy tells you about its history. We still need your help. If you've got time to go to Galaxy Zoo, then please do. Sometime this week, I think Thursday, our time down here, we're going to put, for the first time, images from JWST into Galaxy Zoo. So you'll be able to see galaxies from JWST that no one else has ever seen. Because we know that no one else has looked at these images yet. I'm probably not supposed to have told you that because we're launching it later in the week, but I strongly recommend going to Galaxy Zoo later in the week. But what we thought we were doing with Galaxy Zoo was asking people to sort galaxies into known categories, into spirals and ellipticals, the big types of galaxies that we knew about. But people are distractible, and people are capable of surprise. And one of the things that happened was that the volunteers started noticing that occasionally in the background of one of these images, you'd see a green blob. And they were collected on the project's forum. There was a thread that was called Give Peas a Chance, because they're small, round and green, so obviously they're peas. And then this is the internet, so there's then about 40 posts which are just puns about peas, which meant that all the professional astronomers ignored this thread. But gradually the volunteers worked out that these things were common. They were green because this is actually the glow of oxygen, and the oxygen is a signature of star formation at these wavelengths. So these are all galaxies that are forming stars rapidly. And in fact, we've gone on to work out that the Ps are the most efficient factories of stars in the local universe. So they're dwarf galaxies. They're about a tenth the size of the Milky Way, tenth the mass of the Milky Way, but they have star formation rates that can be 1,000 times bigger than our galaxy. So for some reason, these galaxies have suddenly decided to start turning all their gas into stars. And what's interesting is they tend to live in the empty bits of the universe. They tend to live in the voids. And so one theory is that all galaxies go through this phase. It's just that here in the suburbs of the universe or in the big cities of the clusters and megaclusters, this happened 13 billion years ago. So these are the equivalent of the red dots that we're seeing in JWST, but we're catching the last stragglers who have only just cottoned on to this star formation thing locally. The other thing about the Ps is that once you know they're interesting, they're easy to find automatically because they have a distinctive shape and a distinctive color. But we needed somebody to tell us that they were interesting. And so what we've started trying to do is combine human and machine classification. So where we have the human volunteers tell us what's interesting. For example, we ran a project, a version of Galaxy Zoo, where we just said, instead of classifying the galaxies, we just showed you randomly selected galaxies and said, click on which ones are interesting. And we've also built a tool that if you've got an interesting galaxy, we have a machine learning routine that can go away and find you similar galaxies. So the idea is if you found one P, you would then very quickly be able to find many more. So it's sort of enabling serendipity at scale, which I think is really exciting. I've got into this as a sort of generic way of trying to find anomalies in the universe. And it was only when I was talking to a friend in the pub that they pointed out that if you're looking for anomalies in the universe, whether you mean to or not, you're also hunting for aliens. Because some of the things that would count as anomalous are things like alien spaceships that are passing by. And of course, this is obvious. And people do this for a living, particularly in the radio. This is the Green Bank telescope in Western Virginia in the US. It's a deeply strange place. It's interesting to visit, but for about 100 miles around, no one is allowed to have any device that emits radio waves. So if you live there, you can't have a microwave. You can have a mobile phone, but it's pointless because there are no mobile phone masts. My favorite example is that there's a supermarket that had to install a Faraday cage. So they put wire in the building so that they could use their scanners at the till. because otherwise they might emit radio waves. So it's a beautiful, quiet space maintained, admittedly, mostly for the military installation that's around the corner, but it's useful for radio astronomers as well. But Green Bank now spend about 25% of their time on what's known as SETI, the Search for Extraterrestrial Intelligence, via the Breakthrough Listen program, which is funded by Yuri Milner, who's a Russian, Israeli, American billionaire. But Breakthrough is an interesting attempt to do SETI at scale, to try and use some of the biggest telescopes in the world to listen mostly to stars where we know there are planets and try and look for signals. And they announced last year that they'd found a signal, called it BLC1 for Breakthrough Listen Candidate 1, and it appeared to be coming from Proxima Centauri, from the nearest star to us. So this is the signal. So this is one of these waterfall plots again, other way round. So we've got frequency here and time here. And the signal is this yellow thing that you can see in each of these plots. These are 4 different observations. And this passed all the tests that you'd expect for a SETI signal. So the first thing is that it's narrow in frequency, which at least means we don't know of an astronomical object that could have produced that. So either this is something new astronomically, or it's an alien signal. The second thing is that it only appears when you point the telescope at Proxima Centauri, which seems silly, but it's a good check. The radio sky, as we know, is noisy. And so they do a procedure where they look at a target and then they nod the telescope like this. And you check that your signal appears, disappears, appears, disappears, appears, disappears. And that happened here. And then the really exciting thing is that it was shifting in frequency over time, which might seem a bit odd, but it's shifting in exactly the way that you'd expect if something was in orbit around Proxima Centauri. Because, of course, we wouldn't expect an alien signal to come from the star. We'd expect it to come from, I don't know, a planet or a Death Star or something in orbit around the star. Who knows? So it passed all of these tests. And they spent, that was 2019. And in 2020, they observed again, and they didn't see anything. And so that's obviously disappointing. But they wanted to work out what this was. And they ruled out there's no known source. There's nothing on Earth that produces radio waves at this frequency deliberately. They checked satellites, and they couldn't find a match with any known satellites. They sent people out with radio transmitters to walk and drive around surrounding highways and so on, to see if they could get a signal from somebody's phone or something like that, without any luck. But what they did next was they went through the archive and looked for similar signals, and they found other signals from different parts of the sky. And so their best guess is that this is a malfunctioning piece of radio hardware a few hundred miles away that had been emitting, which is not a great end to a story, but this is still the best SETI candidate that we've had so far. But there's an in-banked assumption in the search that they're doing. I said that it was exciting because it was a narrow band. It was just at a particular frequency. And that comes from this idea that if you see a signal like that, it might be interesting astrophysically. But it's also, I think, slightly old-fashioned because it comes from a time where we were limited by computer resources, and these are easy things to look for. And so what's nice is that people have started to think about new ways of doing searches for extraterrestrial intelligence. For example, using this telescope, which is Veritas in Arizona. This is a Cherenkov telescope that looks for flashes of light caused by high-energy particles hitting the Earth's atmosphere. But they've also started looking for flashes of light that might be lasers used for communication around nearby stars. They probably won't find something, but isn't it cool that they're looking? And there's a large number of people thinking about how to do SETI this way, although none of them quite as creative as my friend Alex in St Andrews. Alex is, I think he's an optimist, though it's sometimes hard to be sure, but he also would describe himself as incredibly lazy. And so while everyone else is doing SETI, the search for extraterrestrial intelligence, Alex has invented the WETI Institute, which is the wait for extraterrestrial intelligence. And the idea here is that any aliens worth talking to would be much more intelligent than us anyway, so we might as well just wait to see if they're getting in touch. And there's an app you can download. If you've got an Android phone, you can download the WETI Institute app, and it waits several million times a second and promises to tell you if it finds anything. Yeah, the point is that thinking creatively is good. I am going to have to skip some of this. Yeah, let me just finish quickly with the last couple of stories. So we can think about different ways of looking at aliens, or looking for aliens. But, you know, what I really want, I grew up on Star Trek, right? I still watch Star Trek. Now, I would quite like to see this, or at least its equivalent out amongst the stars, not just a radio signal. Oh, sorry, I meant to correct this one for New Zealand. Not to scale, I think, but at least the moon is right. But when you start thinking about trying to find advanced life, sort of rather than just technological signatures, the trouble is that you can quickly become a victim of wanting to believe in the famous phrase. So, you know, and the history of astronomy is littered with examples of people who got confused or too excited about something that turned out not to be a mark of intelligence, but turned out to be, really something quotidian. So, for example, observers who saw a nighttime glow on the dark side of Venus that they called the Ashen Light turned out not to be the campfires of Venusians on their holidays. This thing taken by the Spirit Mars rover turned out not to be Bigfoot on Mars, or even little Bigfoot, because it's about this size. It's a rock. 19th century astronomers who drew this vast canal network on the Martian surface. The canals of Mars turn out not to exist. The hexagon on Saturn is very cool. This is the North Pole of Saturn viewed in the infrared, but this is also not an artificial construction. This is just fluid dynamics at work. You can even do this on a grand scale. If you plot the first people to plot a map of the nearby galaxies discovered this, and this is not a giant cosmic stick man. This is just the cosmic web again. And my favorite is that when people found gamma ray bursts, high energy explosions coming from the distant universe in the 1980s, people seriously proposed that what we were seeing were warp drive. And in particular, more recently, when the first interstellar asteroid, Oumuamua, came through the solar system, it was a fascinating event, the first time we've been able to see something that came from another star system, but it's not an alien spaceship. It is unusual. Oumuamua is a fascinating object. This is an artist's impression, but it shows that one of the things that people thought was unusual about it was that it's cigar-shaped. It's at least 6 and maybe as many as 20 times longer than it is wide. And it was tumbling end over end. Characteristics that made it rather different from other asteroids in the solar system. And it had been identified as interstellar because we'd seen its trajectory. We actually caught it on the way out of the solar system. That said, I think this image is absolutely everywhere, but it's worth remembering that it's an artist's impression. I will show you the best picture we actually got of Oumuamua as it passed through the solar system. Prepare to be amazed. I added the circle. We never saw it as anything but a dot, so you have to go from that to that. And a lot of thinking goes from that to that, but I wouldn't, put my house on the fact that that's what it looks like. Of course, because it's a dot, we can measure its brightness, and we did get to observe it for a few weeks, so actually we go from here, not directly to here, we go from here to here, because everyone loves a graph. This is the brightness of the object over time. And it varied a lot for those who were observers. This is 22nd magnitude, this is 25th. So over the course of 12 hours, it changed by about 3 magnitudes. And so this shape, this changing brightness is why we think it's long, because sometimes you're viewing it this way and sometimes you're viewing it this way. And also, we can fit the structure by it tumbling. So there is logic behind this. But we sadly didn't get this image. It also had other mysteries. For example, we'd always expected that interstellar objects, of which we think there are approximately 1,000 trillion of these things traveling through the Milky Way. At any given moment, there's probably one this side of Neptune. We're just not very good at finding them. And we'd always expected them to be comet-like, because in our solar system, the stuff on the outer edges, out by Pluto, is comet-like. They're icy bodies, and those are the ones that it's easy to lose to interstellar space. But Oumuamua resolutely refused to behave as a comet. And we don't know why. People have proposed all sorts of things from, yes, it was an alien spaceship, it wasn't, to the fact that it might have been a hydrogen iceberg, to the fact that it had been changed by its journey process, so there is ice, but it's underneath this dark coating. It was also a very dark object, to perhaps something to do with the structure of the thing. But the trouble with these things is that they come in fast, and though we're hoping we'll discover more of them in the near future, we won't get to see pictures. Except that we've got one chance. We're building a European mission called Comet Interceptor. And Comet Interceptor, it's kind of a good sci-fi name for starters. Sorry, I should have said it's a European-Japanese mission now. And Comet Interceptor is going to launch towards the end of this decade. It's going to put 3 spacecraft in orbit, and then they're just going to sit there. And they're going to wait for something interesting to come by. Because every comet that we visited in the solar system, we've had to know its orbit before we launched the spacecraft. And so we've only visited comets that have been around the sun many times before, so we've never seen a pristine comet. Comet Interceptor, the idea is we'll sit there and at some point in the 10-year life of the mission, we'll see something coming in and we'll go. And we'll get a glimpse of something fresh. Or we can go to one of these interstellar visitors. And I hope that they will surprise us. Of course, you have to find the object on its way in, and for that we have new technology coming as well. I'll end by mentioning the Vera Rubin Observatory. This is an 8-meter telescope being built in Chile. This is the observatory, which is going to scan the whole sky every 3 nights. It'll give us our deepest images of most of the sky, and also every single night we think it will send out 15 million alerts of things that have changed in the sky, from asteroids zipping by to interstellar objects, to the twinkling of variable stars, to maybe even seeing nearby galaxies flicker as material falls onto their black holes, to supernovae, to gamma ray bursts, to the equivalents of the fast radio bursts, which are sometimes seen in the optical. It's going to be an immensely rich and gorgeous data set, but what I'm really excited about is that in there, because it's a new way of looking at the sky, I hope we'll be surprised once again. Perhaps when I come back in a few years' time, if you'll have me, I'll have a pile of new, unusual and surprising things from this telescope to tell you about. Thank you very much. And if you liked all of that, there's a book coming out in February that's got many of these stories and lots of others in. And the cover might look like this. I'm not supposed to have shown you the cover, but there you go.
Thanks very much for the interesting talk as usual. Are there any questions from the audience?
I had something recent. There was a recent paper about symmetry gradient, or the study of a million remote galaxies, dividing them into 4 galaxies, pseudo-constellations in a tetrahedral shape, and finding a handedness bias. You've got a comment on that?
Yes, I have. I've genuinely got an hour-long talk on the topic, but I'm just going to pull something up while I talk. Yeah, this was originally a Galaxy Zoo result. So one of the things we asked in Galaxy Zoo was that we asked people which way the spiral galaxies were spinning. And we did that because somebody had published a paper that said there were more anti-clockwise than clockwise galaxies in the universe, and it was a result that we didn't believe. And so we thought, well, we've got 200,000 galaxies. And so we thought we could test this. And we found that there were more anti-clockwise than clockwise galaxies as well, which is a result that makes no sense whatsoever. Because how do you coordinate the universe so that there's a preferred direction? It was really, really quite disturbing. And so we thought we'd better check this out before we ruined our reputations. And so what we did was, without telling anyone, myself and my office mate, Kate Land, flipped all of the images in the site. So whereas we had been showing people images this way around, we just showed the mirror images. And we still found more anti-clockwise than clockwise galaxies. So it's not the galaxies that's odd, it's us. And so it turns out there's a psychological effect. So this is audience participation time. I promise this is a long answer, but it's not a very long answer. All I want you to do is imagine you're looking down on the cat, and decide whether it's rotating clockwise or anti-clockwise. So if it's rotating clockwise, can you put your hand up? A few people, yeah, okay. Peer pressure. How many people think it's going anti-clockwise, counterclockwise? Most people. Anyone seen it switch? A few people. Yeah, if you haven't seen it switch, if you do this, it makes no difference, but it amuses me. So first of all, there's two odd things. One is that how do we not agree on this? And second, I promise there's nothing odd about the figure. What's happening is your brain is making a decision about how to interpret a 2D image in a 3D world. And if you think about it, there are two options as to how those things relate to each other. And your brain will just choose randomly. And so we think what's happening in our study, I like this, I could leave and you'd all still be here an hour later. What we think is happening is that it's easier to see spiral arms one way than the other. Now, the person who writes the papers that you're talking about doesn't agree with me at all, but I think his stats are shoddy. And I don't agree that there's any evidence for this, but it would be fun if it was true. I promise they won't all trigger a mini lecture. You're safe.
Anyone else? Andrew.
Chris, the new observatory you did the end there that's being built, they don't have that many alerts in a single night. They've got lots of plan they have to deal with that many alerts.
Yeah, well, it's a good question. So the first thing that was decided was that the alerts are going to be public, because there's no way we can deal with any of them. So anyone can get access to the alerts. The second thing is that 15 million is too many to wait. I mean, it's bad enough when I wake up and I've got emails and things. I don't really want 15 million alerts on here. So there's a set of software called brokers that are running, and you can give them rules and then they'll obey the rules. So that you might want to do things brighter than 14th magnitude visible from Auckland or something like that. So you'll be able to filter that way. And people are putting a lot of effort into filters for particular objects. So one example is there's a type of supernova called a type 1a supernova, which are used to measure the expansion of the universe. And in the first month and a half, the Rubin Observatory will discover more type 1a supernovae than in the rest of human history. And so people are building filters to find these type 1a supernovae, and then you can have your type 1a supernova feed. The trouble is that all my weird stuff is going to get junked. Yeah, and so we're looking at ways to, so I think there's a longer answer to this, but we think we can use machine learning to find the most unusual things, and then we'll need volunteers to find which of those are interesting and to do follow-up. So it's sort of a split machine-human task, and it'll be interesting to see how we survive once the data starts flowing. This could be fun.
I've got one mundane question.
Sure.
To do with the Rubin Observatory. There was much talk about Planet 9. We've settled the question.
Yeah, it should do. So Planet 9 is this putative proposed planet in the outer solar system that I think would be about the size of Neptune, or the mass of Neptune, but much further out than Neptune and further out than Pluto. And there are things in the outer solar system that make more sense if there's another giant planet out there. And it's slightly surprising, but true, that you could hide a Neptune out there and we wouldn't have found it yet. We don't have a deep enough image of the sky to find that, but Rubin will build one up. So within the first couple of years, we'll know whether Planet 9's there or not. There are slightly crazy ideas around, and I like a crazy idea. So some people have said, but it might be a black hole that's the mass of Neptune, and that'll be harder to rule out, but it's a bit chocolate tea-botty. I don't see any reason to have ordered a black hole for the outer solar system, and so yeah, I guess that could be there, but I think that's less likely. There are also people who know the outer solar system who think it's already ruled out. There's a big argument going on, but Rubin will settle it one way or the other.
How far out is far out?
I knew you were going to ask that. Is Neptune's about 100 AU, is that right? Does anyone know? 30. 30, yeah, so it's 10 times. So it's about 300 AU would be Planet 9, so about 300 times further out than we are. No, so it's inside the Oort cloud, but out beyond anything that we know of in the Kuiper belt at the minute. So it's the orbits of lots of the outer Kuiper belt objects seem to line up on one side of the sky, is the first order version of the story. And so you therefore need something that scattered them into that position, and you can do that by putting a giant planet out there. However, we also know that lots of planets in solar systems are lost because we see free-floating planets, lots of them observed from Mount John. And so how you get a planet to form and then go out into the outer solar system and stay there is difficult. But the Planet 9 people are really convinced that they're right and have good theoretical arguments. So who knows? It'd be fun to find a new planet. Can you imagine the argument about what to call it?
Did I hear correctly you're talking about Green Bank and you said 25% was funded by Uri Geller?
Oh, no, Yuri Milner. Although, would it be fun if it was Uri Geller? Yes. My only run-in with Uri Geller was that he dreamt that my football team's rivals were going to get promotion, and to help them, he sent the actor who played Darth Vader to assist in some unspecified way. So, you know, if he'd rather play Facchetti instead of that, then I'm all for it. But no, Yuri Milner is the benefactor.
Yeah, so I've heard about, so that's following up about the Planet 9 and the observatory. What would you think is the probability of the Planet 9 being the hypothetical planet that got ejected outside of the solar system by Jupiter or Saturn's gravitational pull?
Yeah, I think it's certainly true in the early universe, all the planets interacted gravitationally. So, as it sounds like maybe you know, lots of the Uranus and Neptune were pushed further out by Jupiter and Saturn, and may even have swapped places. There were some ideas that would have happened early on, which is kind of mind-boggling, but true. So I think that sort of effect would have happened if Planet 9 existed. The trick is, how do you give it a big enough push that it ends up in the outer solar system, but not a big enough push that it keeps going? So it's quite a tricky thing to do. Of course, we don't really understand the details of planet formation. We don't really understand quite what was going on in the disk. So I think Planet 9 would teach us a lot about that stuff if it exists. But yeah, Jupiter, to first order, everything in the solar system responds to what Jupiter's doing. And so that's definitely part of the answer.
Got a question from Nevin on the live stream.
Hey, Nevin.
I've got a question too. You go first.
Okay.
I know you already touched on it, but all this hype about the James Webb seeing high redshift galaxies at highly evolved, is that legit, or is it just a speculation, or is it?
Yeah, I think it depends on your definition of highly evolved. It's certainly true. So the things that are unusual so far is that there are more of them than we expected. That sort of goes with the fact that they are brighter than we expected, which means they've got more stars than we expected. So they're evolved in that sense. And then there are indications that maybe not in the first billion years, but heading back there, we see large black holes earlier than we thought as well. So in general, the universe seems to have grown up faster than we expected. All of that seems true. However, I think the next lesson that's coming hard on the heels of that is that whenever people have had time, and this is only just beginning to happen, to study one of these systems in detail, to look at its chemistry, to look at what type of stars are forming, they're beginning to tell quite a complicated story, right? So at the minute, we've done the equivalent of taking our million local galaxies. Okay, all we're going to care about is how massive they are and how many stars they're forming now. But obviously, you'd miss out whether it's spiral or elliptical, whether it's had a merger, what's going on at the center, whether the black hole's active or not. We need to disentangle the rest of this stuff, and that's now happening because JWST is in a mode where we're now going back and following up some of these galaxies and getting spectra. But it's going to be a really exciting year or so.
Yeah, this is from Niven. He says, thanks Chris, appreciate you coming all this way. If you could have a week on any telescope, which one would you choose and what would you look for and why?
Well, I have a stack of proposals. A week is interesting because that's a lot. I want to do, this answer will change so the answer is going to be JWST, I think. You can give me a week on JWST. And I know what other people are doing. So people are doing deep field. I think a JWST survey of the Andromeda galaxy would be amazing. There's a Hubble survey called PHAT, the Panchromatic Hubble Archive Treasury, Andromeda Treasury Project or something, PHAT, which is telling us a huge amount because we get to see this galaxy in detail. And adding infrared to that would be amazing, and no one's going to do it in the near future because it's a lot of time. So I think one answer is JWST, but I'm still essentially the kid with a 6-inch telescope trying to make a discovery. And one of my biggest regrets is that I was filming at the Palomar Observatory, the 200-inch telescope. It's like five and a bit meters. And it turns out that the Palomar 200-inch is the largest telescope that has an eyepiece that can be attached to it. And we finished our filming, and Saturn was above the horizon, and no one else was booked to use the telescope. And we persuaded them to let us look at Saturn through Palomar, but while we were setting up, it clouded over. So I don't need a week, but if I can have half a night, I want to see Saturn. I did talk to somebody who said that he'd looked at Mars through it, and I said, what does it look like? He said, you realise that Hubble is a small telescope. So yeah, so there's a useful answer and a sort of bucket list answer for you.
I just had one other question related to the Green Bank Observatory. They're bringing Elon Musk.
Oh yeah.
Are they concerned by what's going on?
Oh yeah. No, the number of satellites, which isn't just Starlink and SpaceX, although they're currently the big problem. So optical astronomy is in trouble. With Rubin, it's a big problem. So we think something like 20% of the images that Rubin takes will have a Starlink satellite passing through. And this is a telescope that we built to see faint stuff. So you don't just get the satellite, you get ghost images that are quite hard to predict. So you get the track, but you also see it coming up in other places. So we think we have to spend, the Rubin project's spending about $1.5 million to write software to try and get rid of these things. And we think we'll have to extend the survey by a year or two to get the science that we wanted. But the radio astronomers are in real trouble. Particularly, not necessarily Starlink, but modern satellites are cheaper, smaller, and use off-the-shelf components more. And so they're less reliable at sticking to the frequencies they're supposed to be emitting at. And so, it's a really big worry. We're building a very big radio telescope in Western Australia and Southern Africa. It's called the Square Kilometre Array. And that'll take 10 years we've got bits of it working already, but it'll take 10 years to ramp up. And I'm seriously worried that all that we'll see is noise from satellites. So it's a big problem. But the solution is that we need regulation so that the satellite companies have to comply with, there are already international agreements that say you shouldn't be transmitting outside of particular bands. So we need better enforcement of that from government. So luckily politicians will solve it all and then we don't have to worry about it.
No, I just wanted to say, China, how Elon Musk has stuck a whole lot of satellites up. Well, apparently China wants to do it now because I think America's getting all the benefits from it. So they want to get a spot before Elon Musk uses up all the spots.
And Europe as well, and the UK government has part of a. So this is part of the problem is that it's not just one company. Amazon have a plan that, in general, there are approved plans across the world to launch 500,000 satellites.
I think the solution in the future is probably going to be, just to have, the observatories probably based off Earth, maybe Mars.
I mean, in the very long run, that would be good. Yeah, but it's very expensive.
Yeah, in the very long run, but I don't think Earth isn't really a good spot anymore.
Well, yeah, I mean, that's certainly a long-term solution. Yeah, people have talked about putting radio telescopes on the far side of the moon, for example, where they're shielded from the Earth, and maybe it'll be the radio astronomers that will get there first. But yeah, the trouble is that these things are very expensive. And in a world in which it's cheap to get stuff to the far side of the moon, my guess is that's because people are using it for other purposes, and so we may end up taking the problem with us. We don't have a very good track record, as people in this country know, of as a civilization of traveling and improving places that we end up necessarily. So I think it is worrying, but plenty of discoveries to be made in the meantime.
Thanks again.